Okay, so let's explore this a little bit more through a couple more concept tests. So for this example, and for the case ky equals kz equals pi divided by 2a, plot the expectation value of the energy versus k sub x. And on your plot, you should indicate alpha, beta, and the boundary of the first Brillouin zone. So take a couple of minutes, pause the video, take a couple of minutes to do that, and then come back to the video. Okay, so again, our expression for the expectation value of the energy is alpha plus 2 beta times cos kxa plus cos kya plus cos kza. And so for this particular case, the ky and the kz terms are going to give us 0. And so we're just left with the alpha plus 2 beta times cos kxa. So if we plot that, expectation value of the energy versus kx, our 1bz boundary is at, let's put it here, pi over a. 1bz boundary. As we've discussed, both alpha and beta are negative. So let's say alpha is here, and when kx equals pi over a, then I'm going to have the cosine of pi, which is -1. And because beta is negative, that's going to be the most or least negative value of E. So it's going to vary sinusoidally from here up to here, where again this is alpha. This would be alpha plus beta, again beta is negative, and this would be alpha minus beta, and it's symmetrical on both sides, so it goes over to minus pi over a, the other boundary of the first Brillouin zone here. Okay, so now next concept test. Let's imagine that we squeeze the crystal. So I'm going to squish it from all sides, squeezing in the x, y, and z direction simultaneously just by putting it under a lot of pressure. How does this graph change when I do this? This requires some fairly deep thought. So again, pause the video, think about this on your own, and when you're ready, come back to the video. Okay, so there are two things that we have to consider: the changes resulting from the squeezing to alpha and to beta. So recall that alpha is, let's make sure I've got the correct definition. Alpha is the integral over all space of phi star, the atomic wave function centered on the origin, times the crystal Hamiltonian operating on phi centered on the origin. So when I squeeze the crystal, it does not change the wave function, because we're assuming the wave function of the isolated atom, but it does change the Hamiltonian because the nuclei are getting closer together. So that's going to make alpha more negative. So alpha becomes more negative. Beta is the integral over all space of phi star r minus tj Hamiltonian phi of r d cubed r. So now there are two effects here, again, because the nuclei are getting closer together. So maybe I should go back here and explain when the nuclei are getting closer together. Let's say here's the nucleus at the origin, here, and I've got my atomic wave function here. As these nuclei squeeze in closer, they're going to make the potential energy here in this state more negative. So here, a similar thing is happening, but probably more importantly, as we squeeze the nuclei together, the wave function here is going to have a bigger overlap with this wave function, and therefore a bigger overlap with the region where h operating on this wave function. So this is where r equals 0, and this is one of our nearest neighbors. This is tj, nearest neighbor. So this is only non-zero in the regions where the original wave function is non-zero. So as we squeeze it together, there's more overlap, and beta becomes more negative. So there's three effects. One, alpha becomes more negative. Two, beta becomes more negative. Beta becomes more negative. And then three, of course, as we squeeze it, A gets smaller. So if we put all three of those effects together and try to redraw the graph, if A is getting smaller, then pi over A is getting bigger. So I'll kind of exaggerate this. There's pi over A. Alpha is getting more negative. So if it was there to start with, maybe it's now here. Beta is becoming more negative, so it's getting larger in amplitude. Move this up, see what I'm doing. So it maybe now would look like this. So it's a larger amplitude wave that's centered on a more negative energy and that has a larger wavelength in k space. All right.